I'll tell you how the seasons are on the other planets in the solar system. Give it a try yourself. Ask a friend, a coworker, or someone in the family what the succession of seasons on our planet is due to. Well, it is almost certain that most of them will answer you that the seasons are caused by the Earth's distance from the Sun, which varies continuously for a year. Is that right? Is it wrong? Okay, let's say that from an astronomical point of view, it is not entirely wrong. If we were in fact on a planet like Mercury, it might make sense. But the real cause, as long as we refer only to Earth's seasons, is another. Seasons and temperatures on the various planets in our solar system are influenced by a combination of factors, and Earth's is just a special case. Let's try to get clear on this, and then also take a tour around the entire solar system to find out what the other planets do. One of the key features of Earth's mid-latitudes, where most of you and us live, is that there are significant variations in the amount of light and heat the surface receives from the Sun over the year. Many people believe that the seasons are the result of the changing distance between the Earth and the Sun. It would seem logical and reasonable. It should be colder when the Earth is farther from the Sun, but the facts do not support this hypothesis. Although Earth's orbit is an ellipse and not a perfect circle, its distance from the Sun varies from 147 million kilometers at perihelion, the point in the orbit closest to the Sun, to 152 million kilometers reached at aphelion, the point in the orbit farthest from the Sun. This is a difference of 5 million kilometers, or just over 3% of the average distance of 149.6 million kilometers. An absolutely insufficient value in the short term causes significant changes in the amount of heat received by the Sun. To deal the final blow to this belief, there is then the fact that the Earth reaches perihelion, which is supposed to be the hottest time for the Northern Hemisphere, around January 4th, when the Northern Hemisphere is actually in the middle of winter, and aphelion around July 4th, when the North is sweating from the heat. And also, just to cut to the chase, if distance were the determining factor, why would the two hemispheres have opposite seasons? Actually, as we are about to see, the real culprit in the seasonal distribution of temperatures is the tilt of the Earth's axis. The angle at Earth's axis of rotation is tilted as it travels around the Sun is known as obliquity. Obliquity is why Earth has seasons. Over the last million years, thanks to the gravitational action of the Moon, it has varied between 22.1 and 24.5 degrees to Earth's orbital plane. The greater Earth's axial tilt angle, the more extreme our seasons are, as each hemisphere receives more solar radiation during its summer when the hemisphere is tilted towards the Sun, and less during winter when it is tilted away. Larger tilt angles favor periods of deglaciation, the melting and retreat of glaciers and ice sheets. These effects aren't uniform globally. Higher latitudes receive a larger change in solar radiation than areas closer to the equator. Earth's axis is currently tilted 23.4 degrees, or about halfway between its extremes, and this angle is very slowly decreasing in a cycle that spans about 41,000 years. It was last at its maximum tilt about 10,700 years ago, and will reach its maximum tilt about 9,800 years from now. As obliquity decreases, it gradually helps make our seasons milder, resulting in increasingly warmer winters and cooler summers that gradually over time allow snow and ice at high latitudes to build up into large ice sheets. As ice cover increases, it reflects more of the Sun's energy back into space, promoting even further cooling. Alright, but why does the axis tilt cause the seasons? Basically, what happens is this. The Earth orbits the Sun, making one complete revolution in 1 year. Its axis of rotation is tilted, and very importantly, it always points in the same direction, approximately towards the North Star. In summer, the orientation of the Earth's axis causes the Northern Hemisphere to be tilted in the direction of the Sun. The Sun reaches its maximum height above the horizon, up to the zenith in the tropics, and to an elevation of 23.4 degrees at the North Pole, illuminated for 6 months. The days last longer, and the Sun's rays arrive more directly, warming the atmosphere and the surface. During the same period, in the southern hemisphere, opposite the Sun, it is winter. The sun's rays reaching the mid-latitudes are highly inclined and are absorbed by the Earth's atmosphere more efficiently, producing less warming of the ground. The same thing, but in reverse, occurs during the winter solstice, when it is the southern hemisphere that faces the sun. At intermediate orbital positions, the Earth comes to be at the spring and autumn equinoxes, when the axis of rotation is practically parallel to the sun and day and night are the same length. The effect of the seasons is increasingly evident as one moves from the equator towards the poles, because due to the different tilt of the Earth's surface to the sun's rays, the difference in heat absorbed between the conditions of maximum radiation and the condition of minimum radiation becomes greater and greater as latitude increases. What if the Earth were not tilted? Well, in that case, there would be no seasons, because the sun's rays would always hit each place at the same tilt. We would then have a completely different climate all over the Earth. At the equator, the days would be very scorching because the sun would always be on the vertical, while in the latitudes closer to the poles, there would be even colder temperatures. Life would be limited to the temperate belts, where, however, there would be less pronounced temperature ranges than we know. We would also always have days and nights lasting 12 hours, because the sun would always illuminate exactly half of the globe. What do you say? That astronomical geography bores you deeply and that you were promised a journey among the planets? Okay, but it's still about seasons, so don't kid yourself. First of all, so far we have learned that for the formation of Earth's seasons, the tilt of the axis of rotation is much more valuable than the eccentricity of the orbit. That is the difference between the planet's minimum and maximum distance from the sun. But as we are about to see, things are not the same for all planets. There are planets, in fact, whose axis tilt is very small or even non-existent, for which to mark orbital eccentricity then becomes much more important. Such is the case with Mercury, whose axial inclination is only 0.034 degrees. Practically, the small planet revolves around the sun, keeping itself almost absolutely perpendicular to the plane of its orbit, a condition that prevents it from generating seasons as we know them here on Earth. However, Mercury makes its revolution around the sun by traveling along an orbit that is the most elliptical among those of the planets in the solar system. Even the planet's distance at aphelion is 70 million kilometers, while at perihelion it's only 46 million. This means that more than twice as much heat reaches Mercury at perihelion as reaches it at aphelion. And in practice, we can say that Mercury possesses two seasons, one hot and the other super hot. The surface of Venus, on the other hand, experiences no change in temperature. It doesn't matter if you are near the equator or near the poles. Whether it's day or night, temperatures don't change much from the global average of 460 degrees Celsius. Part of the reason is that Venus's axial tilt is only 2.7 degrees, and its orbital eccentricity is also the lowest in the entire solar system. This means that there is not the slightest possibility that seasons could exist up there. The other reason is the presence of a dense atmosphere and enormous atmospheric pressure 93 times higher than we experience here on Earth. In fact, this carbon dioxide atmosphere traps heat and distributes it throughout the planet through winds that circle the planet in less than 4 days. Mars has 4 seasons almost entirely similar to our own, defined by the planet's position along its orbit around the sun. Curiously enough, in fact, the tilt of its axis of rotation is almost identical to that of Earth. But since a year on Mars is equivalent to 687 Earth days or 1.88 Earth years, the average length of each season is about 6 months, almost double that of Earth's. Unlike Earth's seasons, however, the seasons on Mars do not have the same duration because the orbit of Mars around the Sun is more elliptical than Earth's, implying that the planet moves along the orbit with very different speeds depending on whether it is near aphelion or perihelion. For example, Northern Hemisphere spring, Southern Hemisphere autumn is longest, 199 Earth days, while Northern Hemisphere autumn, Southern Hemisphere spring is the shortest season at 146 days. On Earth, winters are cold and summers are hot, but in general, the planet's temperature is much cooler, with an annual average of minus 60 degrees Celsius. And here we come to the outer planets, the gas giants. Jupiter has an inclination of its axis of rotation of only 3 degrees, and has a very dense atmosphere, being one of the gas giants. Its path around the Sun is discretely elliptical, with a difference between aphelion and perihelion of 75 million kilometers. That sounds like a lot, but it is only the 100th part of its average distance, so the temperature change is minimal. Jupiter is always very cold. The very dense atmosphere keeps the cold temperatures very stable. In practice, we can say that Jupiter has no seasons. In contrast, Saturn's axis of rotation is tilted almost 27 degrees to the plane of its orbit. The Lord of the Rings, therefore, also has seasonal variations, albeit minimal due to the modest amount of heat that reaches it from the Sun, which is on average 1.427 billion kilometers away. With a slight difference from Earth, here each season lasts about 7 Earth years. The planet, in fact, completes one of our evolution every 29.5 Earth years. Right now on Saturn, it is summer, a season that began in 2017. In 2025, autumn will begin, and in 2032, winter. But the changes in the eyes of an outside observer will still be almost imperceptible. Exactly like Earth, Uranus also has 4 seasons, but that is the only thing in common. Because to begin with, the length of Uranus's seasons is very different. If Earth takes 365 days to make one orbit around the Sun, Uranus takes 84 years instead. So Uranus's seasons last roughly 21 years each, but that's not all. As with Earth, it is the tilt of the axis that determines the alternating seasons for Uranus, but again, in a very different way. The tilt angle, in fact, is almost 98 degrees, which means that the planet orbits the Sun practically rolling on the orbital plane. In doing so, it happens that Uranus alternately turns its poles to the Sun, and for as many as 21 years, the winter side never sees the Sun, while the summer side is constantly illuminated by it, and vice versa. But there are also intermediate seasons, such as spring and autumn, during which day and night alternate in a similar way to Earth's, but with the difference that a day on Uranus lasts only 17 hours and not 24. Right now in the northern hemisphere of Uranus, it is late autumn, and in 2030, winter will begin. Neptune's orbit is almost as circular as that of Venus, but the planet's axis of rotation has a tilt of about 28 degrees, which allows even the farthest of the solar system's planet to sport its good 4 seasons. At least nominally, given the cold and enormous distance from the Sun of 4.5 billion kilometers. Unlike our planet, however, the seasons do not last a few months, but roughly 40 years. Nothing abnormal when we consider that the length of a Neptune year, the period it takes to make a full circle around the Sun, is equal to 165 of our years. Right now it is winter for Neptune's northern hemisphere, which began in 2005. In 2046, spring will begin. Further out there would be more to talk about the seasons of the dwarf planets Pluto and Eris, as well as those of the large moons of the gas giants. Do the moons of the solar system show anything like seasons? The short answer is yes. The longer answer is that it is the presence or absence of an atmosphere that matters. Why is that? Well, basically because all the larger moons rotate around axes that are almost perfectly orthogonal to the orbital plane. And so for none of them does the axis tilt factor come into play, in which case the only cyclic weather variations can only be driven by the more or less dense atmosphere. For example, are there seasons on our moon? I would say definitely not. If anything, we could say that they are much less pronounced than the seasons on Earth, and for 2 reasons. In fact, the lunar axis is tilted only 1.5 degrees, which does not allow for significant variations in illumination and insolation during the year. In addition, our natural satellite has almost no atmospheric cover. For this reason, the greatest variation in weather conditions on the surface comes from temperature changes between day and night. These diurnal variations dwarf any seasonal variations, making them imperceptible and unlikely to be measured. Even the Earth, if it did not have an atmosphere, would experience violent temperature changes similar to those on the Moon, making it very difficult to measure seasonal changes despite having such a tilted axis. On the Moon, the temperature of an illuminated area at the equator is about plus 130 degrees Celsius, and that of a shaded area is about minus 150 degrees Celsius. There is no graduation. A person lying on his back on the Moon would be heated to 130 degrees Celsius on the exposed side and cooled to minus 150 degrees Celsius on the back. On Earth, this temperature swing doesn't happen because of the presence of the atmosphere and oceans. The sun's rays heat the atmospheric gas envelope, which redistributes the heat at a global average temperature of 15 degrees Celsius. In addition, the thermoregulatory presence of bodies of water accumulates heat during the warm season and releases it during the winter. However, no liquid water has been found on the moon. In summary, environmental variations on the moon are not seasonal, but are almost entirely conditioned by temperature changes between day and night. Okay, this may have been completely intuitive and predictable, but what about the other moons? Skipping Mars and its two tiny satellites, we come directly to the Jovian system, where we cannot help but wonder if the large Galilean moons are somehow affected by the seasons. Let's start with the fact that all four of them, Io, Europa, Ganymede, and Callisto, have almost no tilt in their orbital plane, orbit Jupiter in almost perfectly circular orbits, and are almost completely devoid of atmosphere. The absence of these three determinants makes the point immediately. None of Jupiter's large moons exhibit any characteristics that suggest the existence of a seasonal cycle. In fact, as with our moon, temperature variations on their surfaces are mainly influenced by the day-night cycle. For example, on Io, the most active world in the solar system, with hundreds of volcanoes and lava fountains erupting tens of kilometers high, the temperature varies from about minus 143 degrees Celsius on the illuminated side to about minus 180 degrees Celsius on the shaded side. The same goes for Europa, the smallest of the Galilean moons, slightly smaller than our moon but still the sixth largest in the solar system, which has the same characteristics: an almost non-existent atmosphere, an axis of rotation perpendicular to the ecliptic, and a nearly circular orbit. Therefore, there is no form of seasonality in the climate and only slight variations in temperature, with minimums of minus 220 degrees Celsius and maximums of minus 150 degrees Celsius. Even Ganymede, the largest moon in the entire solar system and the only moon with its own magnetic field, has to make do with a climate regulated by daily temperature variations, ranging from a minimum of minus 203 degrees Celsius to a maximum of minus 121 degrees Celsius. The same fate awaits the most distant of the Medicean satellites. Callisto, no seasonal variations and temperatures ranging from minus 107 degrees Celsius to minus 192 degrees Celsius between day and night. To find the only moon, in fact, the only object in the solar system after Earth and Mars that can display real seasons, you have to travel all the way to Saturn and then set your sights on Titan. Titan is one of the most mysterious moons in our solar system, the second largest after Ganymede, with its thick atmosphere and unique geological features. This moon of Saturn is a world that has been attracting the attention of astronomers and astrobiologists for years. Unlike any other moon, Titan actually has a climate model remarkably similar to Earth's, with well-defined seasons and weather conditions that can make for clear, cloudy, very windy, or very rainy days in this remote world. With a surface that has dunes, rivers, estuaries, lakes, and oceans, bearing in mind that we are still talking about an alien environment where the average temperature is minus 180 degrees Celsius. But what determines these seasonal variations? What are the factors that influence Titan's climate and how do they interact? Well, first of all, Titan's axis of rotation is tilted 27 degrees from the ecliptic, and that is enough to form very well-characterized seasons. Not like ours, of course, starting with the duration. In fact, Titan takes 29.5 Earth years to complete a full orbit around the Sun, along with Saturn, of course. So its seasons are much, much longer than ours. In fact, each of them has a duration of almost 7.4 years. The last summer solstice for the Northern Hemisphere occurred on Titan in 2017, and now the satellite is in the middle of its fall season. The Sun plays an important role in Titan's climate, but not as important as it does on Earth. Because of its distance from the Sun, Titan receives only about 1% of the amount of sunlight that Earth receives. But even this small amount of solar energy is enough to determine the Moon's climate. The Sun's energy heats Titan's atmosphere, circulating it and creating winds that can reach speeds of up to 500 kilometers per hour. The Sun's energy also determines Titan's weather patterns, including clouds, rain, and storms. But that's not all. Titan also has an incredibly dense atmosphere, composed mostly of nitrogen with a small amount of methane that can play a crucial role in regulating its climate. And when we say dense, we mean that Saturn's large satellite surrounds itself with a gaseous envelope that at ground level is as much as 1.5 times the pressure of Earth at sea level. In the entire solar system, Titan's atmosphere is only less dense than that of Venus. The same layer of nitrogen and methane also regulates the amount of sunlight that reaches the surface, filtering out harmful ultraviolet radiation that could otherwise damage any potential life on the moon. At a temperature of -180 degrees Celsius, the methane in the atmosphere condenses and becomes liquid, resulting in precipitation that forms rivers and lakes on the surface. It should also be noted that rainfall on Titan is not as frequent as on Earth, but when it does occur, it can be quite abundant. Needless to say, Titan is the only object in the outer solar system and the only moon besides our own that a probe has never set foot on. No spacecraft has visited Triton since Voyager 2 flew by in 1989. We're talking about the largest natural satellite of Neptune and one of the most massive in the entire solar system. In fact, the seventh after Titan, the Moon, and the 4 Galilean moons of Jupiter. Triton is also the only large moon to orbit its planet in a retrograde motion, at an average distance from Neptune of about 355,000 kilometers and in just under 6 days. Because of its retrograde orbit and its composition, which is similar to that of Pluto, it is thought that Triton did not form together with Neptune, but is an object from the Kuiper Belt that was captured by the most distant planet in the solar system. In other words, a close relative of Pluto, which it shares many surface features. In 2010, telescopic observations from Earth confirmed the existence of seasonal cycles on Triton that alternate every 40 years. When Voyager 2 visited Triton's southern hemisphere, it was spring. Now, with the summer solstice occurring in 2000, fall should have just begun in the same hemisphere. This is because the satellite's orbit is tilted by 129 degrees relative to the plane of the ecliptic, or 39 degrees depending on which hemisphere is considered north. This means that during the planet's 165-year revolution, Triton will alternately present 2 different hemispheres to the Sun, resulting in an increase in temperature in the illuminated hemisphere. The temperature change between day and night is then amplified by the presence of suspended gaseous material. Triton also has a tenuous atmosphere of nitrogen 70,000 times less dense than Earth's, probably released from the icy surface cover of the same element. During the winter months, Triton's atmosphere condenses and falls to the surface as nitrogen, methane, and carbon monoxide snow. During the summer months, when sunlight strikes the surface more directly, a thin surface layer evaporates, reforming the gaseous layer. Weak seasons, barely noticeable, but with documentable environmental changes. This, dear friends, is all we had to tell you to complete the discussion of how seasons appear on the various bodies of the solar system. After all, only 3 objects, Earth, Mars, and Titan, are those where seasons are more openly manifested. Almost everywhere, the concept of the seasonal cycle is something that can only be detected instrumentally. It is hard to imagine that an object so far from the light and warmth of the Sun, with average temperatures of -235 degrees Celsius, could have the conditions for a climatic cycle to develop. And yet, even at the distance of Neptune, 4.5 billion kilometers away, the force of the Sun, reduced to just 1,000th of what it hits our planet, makes itself felt. But perhaps, who knows, for a microorganism lurking in the ice of Europa or Triton, even a slight variation can mean summer or winter, and ultimately life or death. Don't you agree?